Okay, today, as you can see, we're starting off with some more reactions to go over, and I'm just gonna have to make sure I keep an eye on my microphone. I see I only have one bar left with on it. Then tomorrow, excuse me, with if it's National Education Week, Mrs. Lee had asked if we could do a short activity with elementary as they keep making their way through. So approximately every 15 minutes, we'll have a class come through. And I believe I have just everything that we need, which is we'll have students drop some phenolphthalein within a solution of sodium hydroxide, which is quite basic, and the indicator makes that turn pink, and then the acid from your breath and or carbon dioxide, as you take a straw and blow air through there, the carbon dioxide from your breath reacts with that indicator and makes the pink color turn back to clear again. Now, of course, the science behind that is quite complex. It's just something that we want to be able for them to be able to observe, and then hopefully say, hey, that's kind of neat going into science. I should be like these four ding-dongs. So, which would be good footprints or footpath. A good path to follow is what I'm trying to say, if that makes any sense. So here we have some different reactions, and because of the catalysts, does anything stand out in your mind? Of these four, just let me double check something so I do not lead you astray. Yeah, that's right. So looking at these, I think it's important with everything on the left-hand side of our plus sign. What do these all have in common? I mean, they're all different compounds. Okay, they're the same. What though? Are they four? Oh, they are. I didn't even. And they're all alcohols. Yes. You know, that is a coincidence. That either that or I'm a really good actor since I have that on camera, because I didn't realize I did that, making them all 4 carbons in length. See, told you I had to keep an eye on this. So I don't even know if the sound continues when it starts to blink. So, all right, I usually just do that. It just means 1 moment. We're live again. All right. Yeah, and it still keeps recording. I was going to say make sure that it's still live. All right. So they're all 4 carbon compounds. They're all alcohols, but even though they are all alcohols, is there anything that is different between them? Yeah, yes, 4 carbons. They're all alcohols, but why would that be important though? From last week. We can just go in order. What type of alcohol is this? Even for a Monday morning, I didn't catch you sleeping. How did you know that? Right. When we say X marks the spot, okay, because our functional family is attached to 2 other carbons, then what type is this? And then logic would say that's a primary, and then this one. Okay, so we see all 3 types of alcohols up here. Okay, then what type of reagent is this? if it's dehydration reagent, what about this one? That's what it is, but it doesn't say what the process is. Yep, that's an oxidizing agent. And of course, if this is dehydration, well, then so would those two. Now, look at your catalysts, okay? Or not your catalysts, your reactions. Is there anything different with those? Of course. And what do we see as a difference between these three? Yeah, the temperature range on this one. Okay, so for the most part, with every dehydration reagent or dehydration reaction that we've gone to with these, they've all been at 180 degrees. That's going to give you a specific product each and every time, okay? Now, when the temperature range is different, that is only in that of primary alcohols, okay? Because otherwise this would follow a similar path than this one. When we have secondary alcohols, the temperature range, you're always going to get the same product. With primary alcohols, the temperature range can vary because in one aspect you get an alkene, in the other aspect you get an ether, okay? So it's all dependent upon what type of alcohol you have and then also what temperature range we're at. Okay, so approximately page 390. Okay, so what we see happening when it comes to these alcohols, okay, which one of those, the primary, the tertiary, or the secondary, is the most complex? Do you think, with the limited knowledge that we have so far? Why you're correct. Why is it primary? Okay, and then do we need to be careful with which reagent we have when it comes to oxidizing agents? Yes, we do. Okay, so then as we go further down the line with secondary alcohols, that oxidization, that oxidation isn't quite as complex as that of primary alcohols, and then certainly tertiary alcohols are the most simple. Okay, and why would that be when it comes to oxidation of tertiary alcohols? What does it say on the bottom? Excuse me a moment. And maybe it doesn't say that at the bottom of page 390. I was thinking that it did. Let's take a peek. Okay, where it says tertiary alcohols on page 390 cannot undergo selective oxidation because no hydrogen is attached to the carbon to which the OH is bonded. The OH hydrogen cannot be lost by itself. Okay, now that's what happens with that of oxidation. Okay, so going forward, we can go ahead and proceed with these. Okay. So we have our secondary alcohol, and going forward then, okay, just keep all these the same color. We know this is going to react. It's a secondary alcohol. We're not too concerned about the temperature range, but with our knowledge so far, what happens to all alcohols, okay, when they have a dehydration reagent added to them? They get converted back to what, possibly? Because what does it mean to be dehydrated? What are you losing? Yeah, you're losing water, okay? So one of the things, and you wouldn't be required to do this, but maybe this helps, okay? Because that is half our molecule. Then where might the other half of the molecule come from? Does it come from this carbon, or that one, do you think? It's kind of tricky. I am looking at that. I didn't really visualize this being that difficult just by looking at it on its face. Okay. So let's try this. Let's try making this maybe just a little more easier to see. Okay. Okay, because here we would have 2-butanol, right? Or is it 1-methyl, 1-propanol? Yeah, it's still butanol. And then we would have 2-butanol. So using this logic here, okay, we know that that's going to be stripped off of there. Then what happens? In this case, you have to go one direction or the other. Okay, so left or right. Okay, so once we do that, we took it off the bottom. If we take it off the top now, there's our dehydration reagent. Okay, so these two are now gone. Okay. So we know that that's going to still be single bonded because all three of those hydrogens are still there. Okay, that hydrogen is still there, and then that hydrogen is still there. Okay, and then we can fill that in. Now, what happens between carbon 2 and carbon 3? Okay, we're going to put a double bond in there, just as such. And then, is that it for this product? Or is there anything else we need to do? Nope, that's it. Yeah, because once we count our bonds, this kind of a big space in there. This carbon's got 4, this carbon's got 4, these two, this carbon's got 4, those two, then it's satisfied that way. But that's not the only product that you're going to form. Okay? What might the other one be? Because remember, what did we say earlier? Pick one direction or the other. Okay? Is One Direction a band? Is it a good band? For some reason, that sounds familiar. I'm going to go with no. Is One Direction a good band? I'll take that as a no. Oh, okay. Oh, yeah. I don't know why that stood out in my mind. Probably because I said One Direction. Okay. So if this is one product, then how do we get our other product from here? Right. We're going to put a double bond here. Okay. Change this one back to a single bond. Okay. Which means that has to go on there. And then there's just one slight detail we got to do. Take a hydrogen off the first carbon. Okay. There we go. And those would be your two products. You have butene or 1-butene, and then 2-butene would result from 2-butanol when it gets dehydrated. Okay, then this compound here, recognize what alcohol we have. It's still butanol, it's not 2-butanol. And then what type of reagent is this? Man, we're paying attention. You're doing well for it. Not that you wouldn't. It's nothing out of the ordinary with if we had all 4 here, but with 3 or 4. if all 4 of you are here, we're really paying attention on a Monday morning. So that is potassium chromate, because should you put a 7 on there, then you have potassium dichromate. That makes a big difference, really big difference. Because if this had a 7, okay, that ranks right up there with this reagent. And what is that significance? And it's trying to illustrate that on probably page 390, 391 maybe. Where was it that we left off? Yeah, page 390. What does it show for your different types of reagents there? It just says MnO4 and Cr2O7, okay? One of them is potassium permanganate, and the other one then is potassium dichromate. This, however, is just potassium chromate. So if this was that potassium dichromate, that is going to make a really big difference, because now we said that primary alcohols are way more complex than that of secondary alcohols when they react, and that's true. How many stages does it tell you then on page 390 that primary alcohols go through? It's 2. But that's if the oxidizing agents are powerful enough to do that. This one and this one are. This one, however, is not. Okay? But it still does go through the reaction process. But it can't make its way all the way through the process. So this is still going to react, and it's going to be fairly similar in that of with these powerful oxidizing agents. So in this case, what we're trying to get at, it goes through stage 1 and then stops. So primary alcohols get oxidized, and if it's not strong enough, or even if it is strong enough, it will form which compound after that in stage 1? Yep, forms a carbonyl group on the end. Why is that significant? Yes, because it's a different functional family. So when you say a carbonyl group, okay, so what we see happening then, okay, this got stripped off of there, and then you could pick one of these 2. We'll just go ahead and take this one off. It's a funny looking box, but there is your carbonyl group then. And then, which one? Yeah, then that hydrogen is still there. So this would be fairly similar with that of a powerful oxidizing agent, but that keeps right on going past the aldehyde stage, and then it'll stop once it reaches that of an acid. Okay. So now, what I want us to be aware of is turn to page 399. Okay. It just says the formation of ethers by dehydration of alcohols. Okay. So in a different section, it's saying the discussion in section 13.6 on the dehydration of alcohols to alkenes was an oversimplification for primary alcohols. Heating a primary alcohol in the presence of an acid catalyst produces not only an alkene, but also an ether. So what it does in this sense, I don't think it really says what the breakdown really is. But with this, you have to be aware of, okay, we know this is an alcohol. We know that this is a primary alcohol. We know that this is a dehydration reagent, but the temperature range is different than what we would have seen there and here, okay? But with these 2 reactions, it doesn't make any difference. They're still going to proceed. This one does too, however, but it's going to be a different functional family that shows up or that gets produced, okay? Intermolecular dehydration to form an alkene competes with the intermolecular dehydration to form the ether. In intramolecular dehydration, OH group and the hydrogen atom are removed from adjacent carbons in the alcohol molecule. In intermolecular dehydration, the OH group and the hydrogen atom come from two different alcohol molecules. The reaction can be directed toward the production of alkene or the production of ether by controlling the reaction temperature. Okay, and then to me, well, I guess we can keep going. Unlike primary alcohols, secondary and tertiary alcohols do not form ethers when heated with an acid catalyst. Intermolecular dehydration to alkenes is the major product at all temperatures. Okay? Secondary tertiary carbons are too crowded because of the attached substituents to allow pairs of secondary or tertiary alcohol molecules to come sufficiently close together to undergo intermolecular dehydration. The effect sometimes called steric hindrance. Okay. So the main thing to think about in this case, okay, is the way I like to look at it. It's kind of like a, if you could say, a trap. Okay, when you're getting ready to set it, kind of like gopher traps. I think you have to flip them open like this. Okay. Once you flip them open like that and then they slam shut, what I'm trying to say is there's 2 points. The oxygen is going to be your pivot point. Okay? So what we see here, the main concept is, okay, we understand we've got this primary alcohol. We understand this is a dehydration reagent. We understand this is at lower temperatures. So if this is our pivot point, there's 4, yeah. Okay, now typically I suppose we could have put it down here. That would probably make a little more sense. It's still butanol. So what happens then is this oxygen is all by itself. And then what is it showing in that little diagram right under where it says 13.10? The oxygen is in the middle, and then what's on either side of that oxygen? They're going to be derivatives now. Yeah, 2 propyl groups. Now that's in your reaction. In this case, it's not 2 propyl groups, but rather 2 what now? 2 butyl groups. So how and why this happens, okay, I really don't know. Don't be concerned about trying to balance the reaction, okay? As organic chemists, you're not worried about the conservation of mass between the two. So you're not worried that we've got 8 carbons over here and only 4 over here. I suppose there's a way you could balance that in organically, but I really don't see the point. I should reserve that maybe if it is balanced, we'll give that to the juniors for their stoichiometry calculations. Wouldn't that be awful? So it's just fitting for, no, I'm just kidding. I wouldn't do that. All right. So then finally, this last one, what would we call that compound? It's going to be let me try again. It's going to be butanol, but what type of butanol? It's a tertiary alcohol, and how do we name it? 2-methyl-2-butanol. That's right. So tertiary alcohols, those are just a little more complex. Again, we're really not worried about the temperature range. I think for the most part, we just keep these fairly consistent. It's this one that you got to watch out for. Okay, and then when you have a primary alcohol, that's when you get your ether. So in this case, will this reaction proceed because it's a tertiary alcohol? It's kind of a trick question. The answer is yes. The short answer is yes. Oxidation, tertiary alcohols do not undergo oxidation, but they do undergo dehydration. So same thing would apply. The reason we know that is if we put a box around here, okay, what does that mean? We got to pick left or right again, okay? So let's go ahead and put that to use, okay? So then we still have this carbon down here and then that carbon there. We can safely put those on, but then if this gets stripped off of there, which it does, okay, are you going left or right? Okay, so we're going to go left. We're going to go ahead and take this hydrogen off of there. Okay, so he's gone. That one is still there. We already took this OH group off. So then what do we have to do? We need to put a double bond there because we only have 1, 2, 3 on this carbon, 1, 2, 3 on that carbon. There's our double bond. Okay? So the same thing would happen is if you decided to go right instead. Oh, why did I put an equal sign there? Okay. There. So in one case, we get butene again, and I'm missing something. I'm missing. Something is not right here. I don't think we can go that direction. Oh, because we took them off there, didn't we? Okay. Yes, that's correct. You talking? 2, 3. Oh, okay. It's got to come off of there. There we go. All right. And there. Okay. I guess we stripped this one off the second time. Okay. So fairly complex. There's a lot to remember. Okay. So we're not too concerned about these due dates. I have it set for Thursday. Let's worry more about that. I think, I don't know if we're going to get to number 3 yet this week. We'll see how tomorrow goes, but I'll go ahead and hand this out. So we'll catch up to you next time.